Hi everyone, my name is Jiaqi, a PhD student from the University of Utah, and
Here is
today
the
I'm
agenda
going
of
to
this
introduce
talk.
respect,
First, we will
our
give a
reinforced
quick
learning-based
overview of the
HTTPU
DN scheduling
scheduling
problem.
framework.
We will introduce the motivation and the search space of the scheduling problem. Then, we will discuss the details of respect design. Finally, we will give the experiment results of the respect. Given a DAG-based DN graph, the goal of DN scheduling is to find the best pipeline scheduling solution with defined constraints. It targets optimization objectives, such as on-cache memory usage per stage. Consider a basic illustration shown in the following figure, where the only difference between the two schedules is the convolution tool. This variance in scheduling choice impacts the memory caching and the communication cost. From the memory usage perspective, the left schedule outperforms by having balanced memory usage for each stage and the less communication cost. This difference will result in enhancement to runtime and energy efficiency. In order to enhance DN model performance, including execution runtime, energy efficiency, and the compilation runtime, we have conducted tests on more complex real-world models using edge devices, and we have established three optimization objectives. That's peak of cache memory, communication cost, and total memory usage across all stages. Because these factors greatly affect the scheduling performance. With scheduling runtimes, we have dealing with an expensive search space. I would like to show you some runtime results from over 900 different scheduling solutions for model ResNet 152 in 4-stage pipeline edge TPU system. You can see the results in this figure on the right side. Our analysis gives us a few key insights. First, off-chip DRAM usage significantly influences scheduling quality. Besides, the chosen scheduling solution can significantly impact the efficiency of pipeline edge TPU system. In fact, inefficient solution can potentially double the runtime performance. Now, turning to our solution, Respect. It's impressively led us to a near-optimal scheduling solution. You can find it on the left bottom corner on the results bar graph. It's marked in a red star. In this figure, we provide an overview of several widely used graph scheduling algorithms. There are some well-known heuristic methods, like list scheduling and force-directed algorithm. Those heuristic methods can quickly solve the problem in just several seconds. However, they share a common limitation. They lack determinism and can't guarantee the optimality of the scheduling results. On the other hand, exact methods can provide optimal results, but they suffer from high solving runtime overhead. Addition, exact methods also have scalability issue as the size and the complexity of the problem increase. As the problem complexity grows, navigating through the expanding and increasingly complex search space becomes more difficult. The question we now faced with is whether there is an ideal scheduling method that can deliver near optimal solution while keeping solving runtime overhead low. Reinforced learning, or RL, has seen application across various classical combinatorial fields, include constraint-based solving, planning, and hardware design automation. Now, scheduling DN model on edge devices, which is a classical combinatorial problem, also presents an opportunity for RL application. Why RL? Well, RL method can effectively imitate the behavior of exact method, but with significantly reduced inference runtime, making it a suitable choice for our scheduling method. Our design is Respect, a unique RL-based scheduling framework we have developed. Respect mimics the behavior of existing optimal scheduling algorithm. and its training process can be fully conducted on the synthetic dataset. The most considerable advantage of Respect is its ability to deliver near-optimal solution with short inference runtime.
This slide is the overview of the Respect framework. The input should be a real-world DNA model, and the output is the optimized pipeline schedule, minimizing the objectives like the peak memory usage. The key strength of the Respective lies in its ability to mimic the behavior of the exact approach to deliver near-optimal results, while maintaining a short inference runtime. Taking graph embedding as the input, Respect uses cosine similarity to train the RL agent based on synthetic dataset. In our process, the first step involves embedding the input model. Here, we focus on two key attributes: graph structure attributes and the operator attributes. Graph structure attribute consists of the absolute and the relative coordinates. Absolute coordinates register the topological order of every node, reflecting the viable scheduling space. To calculate those, we use an as soon as possible policy. The relative coordinates contain the parent's ID and the parent's topological level. They are used to uphold the dependence constraint. Operator attributes record the information of every node. For example, it includes the memory consumption for each operator. After embedding, we then feed the vectorized input graph to our RL agent. In a word, the objective of graph embedding is to transform the node attributes and the data dependence constraint into a vector representation, which is the key information to build an RL model. In our approach, we employ the cosine similarity as a reward function as our RL agent. It measures the similarity between our model's output and the ground truth label. As shown in this equation, a small constant number is added to ensure the validity of the equation during training. After the inference process, we perform some post-inference adjustment to match the hardware domain knowledge. Specifically, we correct the dependence violation between every stages. The embedding dataset is the input to our RL agent, featuring an encoder and the decoder. Each of them comprise 128 LSTM cells, as illustrated in the red figure. The encoder processes the queue of node input and converts them into the context sequence that captures every node's information. The collection of all of the context from a reference matrix used in the decoding stage to pick nodes. Using the context information, the decoder generates a selection probability distribution across all candidate computation nodes. We further deployed a point network architecture into an attention network. Point network has proved to be highly effective in resolving various graph-based combinatorial optimization problems, such as the traveling salesman problem. This slide is the overview of system integration. In our system, the first step involves the DAG generator, which extracts the DNA model structure to form a DAG. This includes important details such as the operation nodes, edges, and tensors. Following this, Respect method uses the derived graph to inference and generate the scheduling solutions. Next, we employ the Google toggle converter. This tool splits and quantizes the model, turning it into a TensorFlow TF-flat model that is ready for deployment. Finally, using the Edge TPU compiler, these TF-flat models are prepared for deployment on the Edge TPU platform. Importantly, we have taken the in-state quantization into account at Respect design step. A significant challenge is lacking training datasets, especially for RL models that deal with graph-based combinatorial optimization problems. To address this, we utilize a synthetic dataset for our RL training. In this approach, we randomly generate the node attributes and compute the ground truth label using exact methods. To balance the data coverage and the graph size for minimize the training effort, Our training computation graphs are consistently sized with 30 verticals with different graph complexity. Graph complexity is the maximum count of incoming edges connected to other verticals. This complexity of training dataset ranges from degree 2 to 6, allowing us to control complexity without needing vast data collection. As for the testing, we use the computation graph from 10 real-world DNA ImageNet classification models that is shown in the red table. In order to evaluate respect performance, we use 10 models as benchmarks, that is shown in the previous slides. We compare respect against the exact method and the official HTTP compiler. The HTTP compiler employs the heuristic method for graph scheduling. For exact method, we utilize the integer linear programming conducted on the IBM Simplex solver. For real-world testing, we set up an edge tpus system with options of 4, 5, and 6-stage pipelining, as shown in the figure. Now let's move to the experimental results. Specifically, respect provide 1.06 times, 1.08 times, and 1.65 times speed up over edge tpus compiler in 4, 5, and 6-stage pipelining. For example, for model ResNet 101 v2 and model ResNet 152, respect provide 2.5 times faster than edge tpus compiler in 6-stage pipelining. The overall scheduling performance comparison is shown in the red figure. Additionally, respect demonstrates considerable speed up in scheduling runtime over both of the exact method and the edge tpus compiler. Compared to the edge tpus compiler, respect offers up to 683 times speed up in runtime while still maintaining the near optimal scheduling results. Furthermore, when compared to the exact method, respect delivers an impressive speed up in runtime of up to 930 times. Taking model ResNet 101 as an example, compared to the exact method, respect provides the scheduling runtime speed up of 135 times with only 1.7 inference runtime degradation. Similarly, respect provides both of the significant solving runtime improvement and inference runtime speed up. Thank you for your attention. We are looking forward to answering any questions.